Welcome to the lecture Digital 3D Documentations in Archaeology. Basic aspects of photo and videogrammetry. Under the term photogrammetry, we understand the approach to digitally derive from a series of photos information about the location and size of objects up to large parts of the terrain and thus make them measurable. The working techniques and methods of photogrammetry are already very well studied, work reliably, and the fields of application range from close-range photogrammetry, aerial photography, and underwater photogrammetry to the evaluation of satellite images. For our field of application in the archaeological context and as a preparation for aspects of videogrammetry, it is sufficient to focus on a specific technique of photogrammetry and to present only selected aspects for it. Here we see an overview of the topics we want to discuss in this lecture. This should help us later to find the individual topics more quickly. With photogrammetry and videogrammetry we can spend years, but here we want to get to know a few important selected aspects to develop a basic understanding of both. We want to deal with a very important method for 3D reconstruction from photographs, the so-called structure from motion method. This means that we move through the area with one eye and take these single shots to derive 3D information from them. This method can be used in terrain, for example. Here we see a multicopter taking several pictures or videos of a person on a bench. Below we see the reconstruction result with the commercial software reality capture, which can perform this structure from motion. On the other hand, we can also use this with, for example, a smartphone or another camera and move into the close-up range and capture structures there. We see here, for example, the skull of a Brachiosaurus in the Natural History Museum in Berlin, which was also reconstructed in reality capture. As we have already learned, this process chain is by no means deterministic and will certainly develop much further in the coming years. So it is absolutely necessary to always save the original data. So let's start by creating many recordings of a concrete situation. The task of deriving geometric similarities from different images showing the same object has a high complexity. At first it sounds a bit strange why we do not want to use all image pixels for this process of finding commonalities, but select only a very small set of pixels relative to the number of pixels. To give an impression for the complexity, for example the time needed, why it is not reasonable or even impossible to use all pixels of an image, we consider the following concrete numerical example based on a realistic flight campaign. We flew the multicopter over the remains of the palace city of Karabalgasun in Mongolia in 2018, capturing 777 photos with a resolution of 4,000 times 3,000 pixels. From consideration of various comparable documentations, this is an image set in the medium size range and at 12 megapixels even represents the lower limit of normal image capture performance with a modern multicopter. So we have chosen a rather simple example. Now unfortunately we can't use all the pixels of the images to make the geometric reference. But why? To understand the overall problem a little, let's look at a concrete numerical example. We have now seen the palace complex as a 3D model and know that we needed 777 individual photos for this. These photos had a resolution of 4,000 by 3,000 pixels or 12 megapixels. If we now leave out all optimizations, we would have to examine each of these photos in pairs with each other once for similarities. That means we'd have to do about 300,000 image comparisons. For each image comparison, we now look for a transformation of one set of pixels into the other. Again, if we don't use optimizations, we would now have to compare all 12 million pixels of one image with the 12 million pixels of the other image. That would mean an estimated 70 billion operations for all comparisons combined. If we assume that we only need 1,000th of a second for one of these operations, we would only have to wait 666 million years until the result is ready. We hold the reduction of millions of pixels to a set of a few thousand features is an absolutely necessary step to find geometric similarities between images. The result with optimizations and these few thousand features fortunately took less than 5 minutes on the computer. After less than 30 minutes, we even got a textured and finished 3D model, to which further steps are necessary. A photo consists of many pixels that represent a color value depending on the incidence of light and the reflection property of the object at the scanned image location. Depending on the shooting position or lighting, the pixels of different photos can differ very significantly. It is also algorithmically too complex to infer the image content solely from the arrangement and characteristics of all pixels. For complexity reasons, to compare two images, we need to drastically reduce the large set of available pixels to a small set of relevant features. For this reason, another strategy has proven to be very flexible, exceptionally fast and robust. Here, so-called image features are identified in images, and their positions and local properties are stored. In a photo, not all pixels are considered, but via a function only a subset, the so-called features, which are determined by one of the numerous feature extraction methods. Subsequently, the neighborhood of an image position is usually described by a descriptor. There are also many methods available for this. Below left shows an example of a Huaztec building captured in 2013 with a GoPro Hero 3 and a Phantom 1 in Tamtoc in Mexico. In order to detect most of the features extracted in one image in another, camera motion must be considered. There are 3 variations of motion that the features must cope with: translation, scaling, and rotation. In reality, however, these movements are often mixed. At the top right, we see the end of the 2-step process. For an image, we obtain a set of all identified features. Each element of this set is a tuple consisting of an image position and an associated descriptor. In the process of SIFT, the region around the feature position is divided into a grid, and the local gradients are determined there, which can be seen at the bottom right. After rotating to the dominant orientation, a histogram of the local orientation is created and stored as a descriptor. As the research of feature extraction already started its beginnings with the first image processing methods on computers, many interesting methods and solutions have emerged in the last years and decades. Especially the field of real-time robotics is a driving force for the development of feature extraction algorithms. In the first step, the images must each be transformed into a set of features. There are numerous methods for this in the computer vision field. All candidates that can be used for SFM must be invariant, meaning independent or unaffected, to an affine transformations such as scales, rotations, translations, or a mix of these. A commonly used feature detector used in various applications such as object recognition, image retrieval, or 3D reconstruction is called Scale Invariant Feature Transform, called SIFT, published and patented by David Lowe. There are several GPU approaches to accelerate this. In robotics, however, where computer vision needs to work in real time, other solutions have become established because of their speed. We have now reduced a set of millions of pixels to a set of relevant features. In order to understand what lies behind these points, we need a more abstract model. It becomes interesting now if we want to bring together the feature sets MII and MIJ of 2 different images, II and IJ, which show a common image section, with the goal to identify the common points and to derive a model from them. To solve this task, we will learn about and apply a form of intelligent randomness using RANSAC. To develop an understanding of model building and the role of chance, we first begin by approximating, for a given set of points, the best straight line representing those points as a model. This numerical example comes from the article by Fischler and Bolles, which is the birth of random sample consensus, or RANSAC, one of the most important methods in computer vision when it comes to matching the same image content from different images. It has a wide range of applications. We are now looking for the best straight line that represents this set of points. There are several ways to approach this problem. With least squares and RANSAC, we have two very important representatives of these possibilities. Let's take a look at a specific task. We are given 7 points, and the objective is to find a line that best represents these points. It's important to keep in mind that our ultimate goal is image matching for 3D reconstructions, where there may only be an overlap for a portion of the respective points. Therefore, it is reasonable to assume that there might be points that do not fit into the model. We refer to these points as outliers. Additionally, we should consider that when comparing two images, features may not always be precisely located in the correct position and could be shifted by a pixel or two, given that we are dealing with raster images. Taking both of these factors into account, everyone should see a very dominant line running from the bottom left point, 0, 0, to the top right point, 4, 4. The most straightforward approach, which we learn in school, is to derive a straight line directly from the points using a functional equation. Using the least squares method, we can iteratively approach a good line fit. Initially, we assume that all points belong to the model of a straight line. In our example, this would result in a horizontal line. Now we can eliminate the point from the list that is the farthest away and degrades the model the most, and generate a new line. We repeat this process until the error tolerance is satisfactory to us. After 4 iterations, the points included in the model are 1, 1, 2.2, 3.2, and 10.2. Here it makes sense to pause the video for a moment to visualize the resulting line. Let's take a look at the results side by side in a visualization. The red line represents the result from the least squares method, and the green line represents the result from RANSAC. The RANSAC result is found very quickly. We had mentioned that we consider all points within a certain proximity to the model as part of the error calculation. In this visualization, we represent this consensus set with the surrounding gray area. From this, we can see that only the point 10.2 is considered an outlier. If we expand the stitching process to include a homography transformation, we can achieve impressive panorama results. For example, the left and right images can be matched and merged into a single image in the middle. The process involves finding corresponding points between the two images and estimating a homography matrix that represents the geometric transformation between them. This transformation takes into account translation, rotation, scaling, and perspective distortions. Once the homography is computed, we can apply it to the pixels of one image to warp them and align them with the other image. Then, the two images can be blended or merged together to create a seamless panorama. This approach allows for the creation of panoramic images by combining multiple images into a single wide-angle view. It provides a more immersive and expansive representation of a scene. Let's take a closer look at the structure from motion process chain, or short SFM, and its overview. The structure from motion approach can be simplified as follows. On the upper left, we see that the observer V1 sees the 3 features P1, P2, and P3, and the observer V2 sees the 3 features P2, P3, and P4. Due to the different position of both viewers, there are points that the other viewer does not see, also named as outliers. At the bottom left, we see the 2 image captures of the respective viewers on the outside and the intersection in the middle. For a successful reconstruction, this intersection must be large enough, and these are the points we are concerned with now. In this set in the middle image, we see the points P2 and P3. Both have moved at different rates. If we have enough points, we can deduce the positions and orientations of the viewers V1 and V2, and thus reconstruct the positions of the points in 3D space. Above right, we see the 3D point cloud as a result of the SFM process. On the right, the resulting mesh consisting of triangles, if the points are connected, for example, via triangulation methods. After the SFM process, there are again numerous options available in the further process to derive textured 3D models from a set of 3D points or the estimated camera positions. We have to be aware that the 3D points we have reconstructed from the photos so far correspond to real points. We will now connect these points via surfaces during surface reconstruction and thus transform them into a textured 3D model. The estimation of these surfaces aims at creating a nice-looking 3D model without corners and edges, and thus we leave reality a bit and focus on the viewer's perception. In photo-based 3D reconstruction, the reconstructed 3D points correspond to reality, but the surfaces in between are fictions and are represented as edge-free as possible for human perception.